Okay, I just Googled a list of longest living organisms. This is a very interesting page on Wikipedia. Um, I can't say I actively follow the work of folks who are doing good work in this space. The individuals that come to my mind are Dr. David Sinclair, Aubrey de Grey, and Dr. Peter Attia. Attia is coming at it more from a human longevity perspective. And I guess the two other names I mentioned also, but I think Dr. Sinclair has more of a kind of evolutionary kind of biology angle to it. Like he has spent, it looks like it's time looking at the lifespan of some of the other organisms as well. Like try to figure out try to peer like look into what are the functional reasons as to why that happens, and then develop therapies and techniques in order to be able to do that for the human system. Most notably his work with the NAD molecules, NAD, and potential other therapies. I'm not like super like I said, well versed with the works of any of these individuals, but I think it's a very interesting subject. And I just Googled this up, like list of longest living organisms. I haven't gone through the whole page on Wikipedia, um, but let's take a look. Um, so this is a list on Wikipedia for some of the longest living biological organisms. The individuals, or in some cases, clones of a species with the longest natural maximum lifespans. So let's click on that thing. Let's see what comes up. So in terms of maximum lifespan, I'm gonna eyeball this. It would be really nice if there was some kind of that's exactly what I was looking for. No, that's a human system. So this corresponds to the body mass index. Um, and let's see in other animals. That's what I'm curious about, because I'm like thinking of what kind of lifespans exist in our universe. I'm really curious and fascinated with that topic. Um, oh, what is that? What is that? NH repository. That's what I want. Hmm. Okay, what's an all aquatic salamander? Okay, Oxytos, something like that is called, right? Oxytos. Wow, this thing can live to 102 years. That is crazy. Wonder why. Wonder why. These are not Creative Commons images, so I don't know if I can. Hmm. Okay, salamander living in caves. Okay, so living in caves meaning, is it living in the dark? And if it's living in the dark, then it doesn't need eyes, right? Because the eyes would have been kind of evolution would have kind of. There are no Creative Commons images. That's a tragedy, travesty. underdeveloped. Okay. Blanding's turtle, 77 years. Okay. It's found closer to where I live. Very interesting. Very interesting. Turtle, 138 years. Rough eye rockfish, 205 years. Wow. Wow. No way. Where do they live? North Pacific. Okay, so it's a saltwater fish. Deep water. Coast of Japan, all the way to San Diego. Hmm. Relatively cool environment, not interacting with the sunlight as much, right? Because if it's living at depths, generally at these depths, a lot of the sunlight and radiation is getting filtered out. I'm thinking I can map feet better than meters in my mind. Yeah, they live near the seabed, over boulders and rocks surrounded by soft substrate, and in caves and crevices. Starting to see a pattern here. Maybe a little bit too little information. They're long-lived aliens that are probably like shielded and they probably evolved in caves or something, right? Or underground. So they must not have eyesight, or their eyesight would be weakly developed, so they would have evolved other senses. We're going with very little information here, so let's not get carried away and go the alien route. Sea urchin. Let's Google that. Sea urchin. Okay. I could never tell if sea urchin is a plant or a. What's the kingdom? Animal. It's an animal. Okay. Phylum. Okay, it's like the starfish kind of phylum. Okay. And order. Echinoida. That's the actual family. And then the genus. And then finally species. I've made the mistake of equating genus with phylum. I've made that mistake in the past. So I meant to say phylum, but not genus. Right? I didn't know there were all these subclasses. Yeah, I'm actually interested in building something like that for life across the galaxy, at least, if not the universe. So this is an animal. Look at this. They have the ability to regenerate lost spines. How did they do this? Wow. Wow, this could change so much for our species if we understand this. This could actually help people that or like my dad actually could help regenerate his cartilage. I have a friend who lost. So if it's regenerating spines, does it also regenerate the nerves around the spines? It must, right? Or maybe the nerves remain intact and just regenerate the spine. Often 30 years, but has been found over 200 years old. What is the source? Well, it links to a NOAA page, but that page is not accessible. I don't know what that means. No, it's not working. Okay, let's go back. I'm just curious what the body looks like. Can I use these images? Okay, well, graphic warning. You're gonna see graphic images right about now. So this is the mouth. That's the genitalia area. It starts with number 1. Gonophore. This is where these eggs, sperm, and other parts, part played with mat, grip, orite. Part number 4. Okay, water enters here. Axial gland, this one. What does that do? Immune system, gonad, and sea urchin eggs. So I would think this is the spine, the blue one. What is this? The green is number 7, number 8. Let's go to number 8. Ampullae. Wait, so it does this to move the water in and out. I think extend the tube feed muscles used to contract the tube and push the water back into the ampullae. Intestine, number 7. Test is the exoskeleton, okay, which is what we see when we look at the sea urchin. Calcium carbonate. So, oh, this is bony. This is a bony structure. It's not. I wonder what it's like to touch a sea urchin. Is it like really hard, or is it like slightly pliable, like the bones in your ears? I wonder what it's like to. Yeah. Radial canal, esophagus, Aristotle's lantern, the organ that chews and ingests food. Where is that? Number 12. Number 12. Oh, that's interesting. So the mouth is somewhere here, but it chews the food here. This is the equivalent of the mouth. And then it goes through the intestine, somewhere here. Right? And teeth. Where are the teeth? Teeth act like jaws. Okay. And what else is there? Mouth, nerve ring. So your urchins can detect touch, chemicals, and light. Wow, they're very sensitive. Chemicals and light. Wow. 15. Okay, something. Is that the black stuff here? The grayish green? Yeah. canal, water, section that formed the test. 17. Okay. So you say there's something. 18, 19, 2 feet. Used for locomotion and move loose food particles towards the mouth. Used for defensive movement. If broken, they can regenerate. Oh, that's what they meant by spines. I thought they were saying like something inside of the structure. But still, like that's a living thing, right? So studying that could help us understand how to regenerate bones. I think I'm like it looks like the same kind of material, right? Anyways, let's get out of here. I think we were here. Ocean Quahog clam, 507 years. No way, man. Hmm. This looks like the oldest animal we have discovered on Earth so far, if I'm reading this right. They even named it Ming or half run, half run. This goes by the development of the rings on the shell, annual growth lines in the shell. Maybe there's some other factor that caused the ring lines to form faster. Oh man, they killed the clown. What? Just let it live, see how long it can live. You use some machine vision to figure out how old it is, or better carbon backdating. Wow, it was born during the Ming Dynasty. That's crazy. Okay, couldn't determine the sex because the reproductive state was spent. So something happened to his reproductive organs after a certain amount of time. It's still alive, but certain systems may not be working. Right? Oh, so that was a mistake. Carbon backdating. Okay. What do they look like inside? Well, that's just a shell. There's nothing in there. I don't know if I've eaten these. I buy them from the grocery store. Mm. Hmm. This seems important. This seems important. Well, first I need to put this in my notes. the actual terms. What that means, it seems. This is where I'm more interested in. Well, I might as well put the foot. Dynamic energy models. Somatic maintenance cost. What does that mean? So intermittent fasting makes sense. And I'm also thinking, well, in the case of torpor, like cryo, it's called deep, when you go to sleep during longer voyages. What is this showing sci-fi? That makes sense. Because by reducing the temperature and the metabolic rate, makes sense. How does that happen? Yeah, I'm going too deep here. I gotta take a break. I gotta go for a walk after. Oh, I was just thinking about that. Hmm. 90 to 180 days. Okay. So 3 to 6 months. Hmm. Let's take a look at this. Mhm. You're gonna do it right. You're gonna do it right. I don't need you. Oh, that's pretty cool, man. That's some serious engineering. By the looks of it. Aquablinker, what's it called? Why you do that? Why you not put this in here? What is this? The water sampler? TRL5, that's pretty good. Um, what happens when the battery runs out? This is going to create pollution because you're not going to extract it again if you're spreading this somewhere. Interesting thing. Quick shot. What is a quick shot? Oh. What? Making a plane? Pretty cool. It's interesting. They do a bunch of things. Honesty is important. Hmm. Yeah, how much does it cost? Mhm. Price. Okay, I'm gonna get out of this. But this is what curiosity. That's pretty cool. I learned about. I was looking at lifespan and I had no idea that NASA was using this for torpor. What's 2-4? Oh, like the collective condition we're all experiencing right now. I'm just kidding. Dormancy. Hmm. This is an interesting thought. Like I've thought about this. Like how do plants survive the harshness? So much sunlight, so much water, like snow, plummeting conditions for temperature, rising conditions for temperature. Plants do this because they have a hard exterior, generally speaking. And then when the temperature is right, that is when the buds and everything start forming. So if we're designing life for the future, we need to keep that kind of design into consideration. And yeah, I'll stop there. But okay, so that was torpor, and I was here. Let's close these. This is very interesting. What's the thing? 5 years, right? 5 or 7 years. Wow. What else is there? What? 5,000 years? No way. So no wonder they named aging institution after this. I think this name comes from the Bible. This is in the first couple of parts of the Bible. I haven't read the Bible completely, but this is like the first couple of chapters and maybe first couple of pages. Metzelay Foundation. Methuselah. Oh, Aubrey de Grey founded this. I didn't know that. 90 the new 50. That's pretty cool. So that means I'll be 90 years old, but I'll look like 50. Man, I want to look 24. I don't like aging. I look pretty good, but I'm in real age is 41. Biological is probably younger because I keep inflammation down. I eat healthy. I should exercise more. I sleep. Take care of my mental health. I can't say I'm doing everything, but I'm doing most of the things. I'm eating the right food groups, generally speaking. I don't eat red meat. Maybe. No. Okay. That's pretty good, man. I hope you guys make a lot of money and I think aging really grew for looking for some funding going back 3, 4 years. So this is pretty good. I hope this has solved the money problem at least. This is the vision we need for the future. We need to think about these therapies because people really suffer in their old age. My parents are really suffering. And I don't want to get into the details, you know, it's the physical suffering, the mental, psychological, and emotional suffering that comes with it. My mom sits at the edge of the couch and she just rocks back and forth. And she goes to the hospital, and the hospital tells her there's nothing wrong with you, right? And this happens every year. It's a cyclical thing, like like she complained. I think there's a psychological element to it. I'm not a doctor. I could be wrong about all this. My father's knee got replaced, and his health just took a nosedive after this. And I think there's some psychological issues there as well. Because my dad watches a lot of TV, and he doesn't want to go for therapy. So it just creates this challenge. And on top of to make everything worse, they keep telling me I need to fix my life. So I'm in this dynamic whereby my parents in their old age is not just old age. They had really good genetics, but I don't think they made the right investments. Particularly my mother, like she ate whatever she wanted, ate a lot of sugar, a lot of carbs. No wonder she's had diabetes for 30 years now. And this just causes problems if you don't take care of yourself. You know? So I'm just saying that. Well, the thing is now, even if the therapies exist, right? the therapies existing does not mean people can keep doing what they've been doing, abusing alcohol and abusing food. And I'm not talking about parents at this point. I'm just talking, you got to take care of yourself for you to benefit from therapies like this. Just like if you go to a mental health practitioner, you can't expect a mental health practitioner that you're going to solve all your problems now and in the future. You got to make the investment yourself. Anyways, I didn't think there's going to be a commentary here, but this is the Methuselah Foundation. Come back to the bristle cones. 5,000 years. Wow. 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 It's a pine. Ah, it's where they grow, I think, if they grow on the certain like higher. That's what they're saying. Look at those roots going in the rocks. Wow. Uh, okay. This is not confirmed, man. That's not true then. 5062. That should be 5073 by now. I did my math right, but it's not. It doesn't seem like this is legit. Okay, Methuselah is confirmed. Okay, all right. So Methuselah is confirmed though at 4852. So, but 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 another tree was confirmed at age 4852. Source. That's good. You probably want to keep it secret because there's going to be a whole horde of these people taking samples from that tree. And the next thing you know, the oldest thing that we know is actually alive on this planet right now is, well, it's not in a good condition. Average 2,000 years. Oh, okay. North-facing slopes, 2,000. I wonder why. Maybe it's the region. Maybe there's been a lot of fire. Those things. Wow. Wow. I wonder what is about the cellular structure that even after they die, they can the wood can preserve for such a long time. Right. So I guess where you live matters, and then I wonder the cellular structure matters. I wonder if these are the same trees that kind of interlock their roots because the earth is not very deep here for their roots to really go in, so they just interlock their root system. Okay, now how much time am I spent here? Okay, let's go back to let's see if there's anything else. Okay, maximum lifespan. Okay. Well, let's start with a fly. There's some mayflies. Mayflies. Lifespan, 24 hours. I think I read this right. It's 24, 36 hours. The whole thing, they are born, they reproduce, they die. 24 hours. Wow. Okay. And then you have the housefly or fruit fly, actually, they're called. Fruit fly, lifespan, I think on average is 21 days. I could be wrong about this. It's 21 to 36 days, right? And then you have all these other creatures in between that. Then this seems to be specific to most living species has one upper limit and the number of times the cell of a member can divide. I'm sorry, most people have at least one upper limit on the number of times the cells of a member can divide. This seems important. Is this the only reason why we age? So let's put it on the lifespan page. Oh no, that's not what I want to do. Yes, that's what I want to do. I want to do. Yeah, there we go. At least one upper limit. And, yeah. Okay, this is called the Hayflick limit. Although the number of cell divisions does not strictly control lifespan. Okay, well, Peter Diamandis talks about the senescent cells. He's like, if we remove the senescent cells, that would be one way to extend longevity. I think they have a human longevity company. I wonder if that's the thing they're looking at. But I would think the cell division stops because the telomere is being eroded or it's really thin. So I don't know the role telomeres play in the cell division, but I forget the name of the guy, Bill something. He said the telomere thing, which he's personally has investigated. He said that was one of the many reasons why aging happens. But I think the telomere aspect is tied directly to this. That's what I'm thinking. Aging at the cellular level, more like looking at the what's it called, the clam. That's what I was thinking. What's going on with the clam at the cellular level? Same with the tree. What about the tree is so a big question. It seems there's so many things to explore in this world, man. This is here. Thesis now. What ought to be and what ought to be done. Genetic mutagenesis. What does that mean? Mhm. So it's being changed. If we have a mouse and we injected a gene in them to make them bioluminescent, that then the mouse would have gone through the process of mutagenesis, right? Hmm. Well, cancer is the irregular replication of cells, right? Let's take a look at that. According to cancer.gov, cancer is disease in which some of the body cells grow uncontrollably and spread to the other parts of the body. Okay. Too much mutation can lead to cancer, or mutation, not too much. In nature, mutagenesis can lead to cancer and various heritable diseases. Heritable meaning? What does heritable disease mean? Genetic disorder. Yeah. Well, I don't know if a boy with a Down syndrome should use power tools, but yeah, I mean, I guess that's a spectrum. I don't know much about Down syndrome. I'm just saying. Um, yeah, yeah, I should not probably make that comment because I don't know. It could be, or maybe the kid should use power tools. I don't know, right? Because just because somebody's got Down syndrome. Actually, I saw this YouTube. There's a girl with Down syndrome. She seemed pretty like it wasn't impacting her life. And so I guess it's a big spectrum. But they're saying mutagenesis, come back to you, is all the driving force of evolution. Okay. Herman Mueller. Hey, I've heard this name before. Maybe when I was looking at the nuclear thing. Yeah. Yeah, I was just looking at this yesterday. X-rays causing mutations. Hold on. Work done by this, but Hayflick is not there. McFarlane Burnett. Yeah, he's just remembered. Looks like a guy. Okay. Primary culture phase 1, proliferating, luxuriant growth. Okay, after months of doubling, the cells eventually reach phase 3, a phenomenon known as senescence, where cell replication rate slows before halting altogether. Okay, let's take a look at this. That's the chromosome. That's what I was saying. It's the telomere. And as the cell keeps dividing itself, the telomere gets less, till a true point comes when there is no telomere. Okay, so if the body has this number of trillions of cells, right? The question is, how many cells are there in the embryo in the first place? So I don't know how you make an embryo. I have no idea. So, but you have the embryo, right? And I, I should know more about the human reproductive system or any reproductive system in that. But you have an egg, right? And then you have a sperm, and then I think that's one cell. Could be wrong. And that is one cell, right? I think I'm not sure. So this cell, this one cell makes a copy of itself, right? that becomes a new human somehow. It's remarkable that there is so much information packed in one cell. That boggles my mind how much information evolution has packed, or however things work, right? Into one cell. That is one cell. Now, this person, no, it takes time because this, no, let's not do the person right now. So this is one cell. And now this cell has made a copy of itself, right? Copy of itself. And so now you have two cells and then four cells. Does that mean the telomeres are getting shorter here as well? No, let's Google this. Oh, that's a good question. I should say something myself. Nature, that's fine. Telomere lengthen during early embryonic development. That's really interesting because we know that, where's that page? We know that telomeres, it seems, shorten during cell division. But this article is saying telomeres lengthen during early embryonic development. Whoa. Okay, my brain's slowing down, but this I'm not gonna put it in quotes right now. Make it nice and clean. Pluripotent stem cells. Pluripotent. Pluripotent. Wow, that's crazy. Yeah, I knew this, but it always amazes me what's going on in this cellular biology. Yeah, one day we can make the entire human again. Put the old brain with the regenerated neurons. So we'll have biological recapitulation within 20 years. I think this will happen. Nobody would die of organ failure, you mean heart disease. We gotta change your habits though. People have broken hearts. Kids, I can't say who, but the kid has heart valve that not developed properly. Okay, I gotta take a break. But I'm gonna go back here. I got sidetracked. Looking at senescence. Senescence. What is it here? Hayflick limit. Lifespan. Lifespan. I was talking about lifespan, right? So I talk about mayfly, then fruit fly. Mouse lives 4 years. Brown rat 3.8 years. Dog 29 years. Some live more than others, depending on the kind of dog. Same with cats. Wow, I had no idea cats can live 38 years. 42. This is the maximum recorded. 62 for horses, 86 for Asian elephants, 100 years up to large parrots. Japanese koi fish, 200 years. Generally 50 years. 26 was the longest living. Tortoise, 190. Reptile species in New Zealand, 100 to 200 years. Eels, 150, 155. Whales, about 200 years. That's horrible, man. Bowhead whales killed recently still had harpoons in their bodies from the 1890s. Wow. Maximum 177 to 245 years. I wonder what happened with the amino acids here. Greenland sharks. 392 plus minus 120 years. Minimum 272, maximum 512 years. So that would be the longest living mammal then. No, are sharks mammals? Seems important. 507 years, Ming, we reviewed this. Jellyfish, exceptions. Hmm. They're able to revert to the polyp stage even after reproducing. So-called reversible life cycle. What does this mean? Polyp. Polyp is a sessile life-changing stage of the species belonging to the Cnidaria phylum. Corals and sea and anemone. A polyp formed by a tube with a mouth surrounding with tentacle referred to as the head, and attached to the bottom with a foot-like disc. Now let's click on the right links. There's some other stuff showing up here. That doesn't really help me. Government of New Zealand. Okay, those others. But I want this to add the word jellyfish. Smithsonian. Oh yeah, this is what I was talking about. Bioluminescence. This technique is also used in other areas, benefiting humans. This seems very important. So it turns itself back into a polyp. Can revert to a polyp stage, forming a new polyp colony under these conditions. Let's document this. I'm not going to look into this in depth right now. Now let's slow down my thoughts and like, why did I think this is important? Because there was some mental construct in my mind where I had I have some representation of cells and different kinds of cells. Like obviously I have this concept of the world that we live in, right? And then I this what I just shared, and what is transdifferentiation? Progenitor means it knows where to go. I think. I'm not going to go deeper here right now. Pluripotent, what does that mean? What is a somatic cell? You gotta take a break. Transdifferentiation. Somatic cell. To an immature somatic cell without undergoing an intermediate program state. Give me examples. That's the way I understand here. The only other rules. Okay, well, handle with care. Whoever may be watching this. Oh, good, 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 good. Well, what's good is open to interpretation as a problem too. Yeah, just calm down and relax. Okay. Wow. Harvest of jellyfish. China's harvesting a lot of jellyfish. Thailand is next. That doesn't mean that China, people in China are eating jellyfish that their lifespan is going to increase because the amount of DNA you actually absorb through food sources is almost negligible. Mhm. That was the page for jellyfish. Yeah, okay, so like we covered a lot of ground in this 1.5 hour segments. Like I wasn't gonna make this a public video. This is just like stuff that I do to better my understanding. I would say that this is a terrestrial snapshot, right? And we're looking at depends across the animal and plant kingdom. We're looking at anywhere from like 24 hours to a 5,000 time frame lifespan. Now, Wikipedia, there are exceptions. Actually, we're exploring this. Let's keep going. Actually, I have no idea what Hydra is. Oh yeah, it was where we started with. Okay, well, this is an animal. I thought this would be an insect. That's what it looks like. Okay. Doesn't age at all. Fascinating. How to estimate the age of a specimen. Hmm. What? Okay, let's save this whole section. Hydra, flatworms, binary fission, cellular division, whatever that means. Flatworms. What do it look like? Oh, it's some kind of sea creature. Hmm. That's really interesting. They get oxygen by diffusion. I wonder how that impacts them on a cellular basis. Wow, that's really weird. It eats and poops from the same place, if I read this right. That's really interesting. Wonder what's going on in cellular structure again, the lobster, or however this all works. I think that's the second time I said that to you. In this video, please. However that all works. Maybe 3 times. Maybe more. Definitely twice. Tardigrades, water bears. Suspended animation. Okay. Yeah, I looked into this before. I think there's something in their structures called cryptocellulose, cryptobiosis. And this cryptobiosis is so how does a tardigrade survive freezing? Because if you freeze a regular cell, then the cell walls rupture, right? So if you are cryogenically preserved right now, your full body, whatever, like using existing state technology, say like somebody's end of life, whatever, like say they want to do cryo, and say the technology evolved 5 years later. No, actually, that would contradict. I think right, the cell walls rupture when you freeze them. Something happens to the cell walls, so a big chunk of that person is going to be all gooey and stuff when you revive them. So for the physiology and obviously the brain, which is physiology as well. But yeah, so this could be interesting. So you have cryptovirus. I thought about this. I think I made some comments about this on Quora. The reason why this happens is there's some kind of a glucose or something. Glucose, fructose, sugar. Yeah, here we go. Invertebrates undergoing any hydrobiosis. Oh, first of all, oh, let's take a look at this. Okay, now, why are you not working? That took forever to load Wikipedia. Oh no, the ice age is coming. Stuff's getting dry. I actually shouldn't go on that right now. It's doing something. It's preserving its functions because are they dropping the temperature? No, they're adding the water again. It's almost like there's 2 eyes here. There's 2 eyes. Desiccation means removal of water, right? Oh, there we go. Life without water. Yeah, I'm marveled how plant seeds can stay alive for years, months, if not years. It's remarkable. That's so beautiful. It kind of looks like the plant for lavender, and there's a herb like this as well. Mhm. Oh no, National Geographic, why are you not allowing me to do this? 'What's the Y radiation? I'm not gonna look into this right now because I don't know why they see they, I don't know if there's some kind of a technique for this. 4,000-year-old lentil. Okay, what's the history for this Wikipedia page? Yeah, it's been updated more recently. So the question is, why is this article from 32,000-year-old tree? This is from 2012. Why is that not there? Thanks. Well, that's a plant and that's a Bible seed. It's still quite okay, is this guy? Baker's yeast. This is what I was referring to. Invertebrates undergoing, and that was a seed segue because of this one. But invertebrates undergoing anhydrobiosis often contract into smaller shape, and some proceed to form a sugar called free halose. A procedure developed in 2017 and using free halose allows sperm storage at room temperatures. I can't wait for synthetic biology to fully blossom. I have so many ideas. We're gonna totally like change, well, for ethical purposes, universal good. Maybe cracked and dried out, but will turn green again and revive because of function of trailer host. That's really interesting. That is crazy. Well, let's go step by step. So this is the page for cryptobiosis. And then, so you learn about trehalose. And within the trehalose page, we were somewhere here. And this seems important to me, and I don't really understand it. Vitrification theory. Vitrification means vitrification. Vitrification provides benefits of cryopreservation without damage due to the ice crystal formation. That's what I was talking about. Cryopreservation. Wow. Man, I gotta stop. I really gotta stop because I gotta review something else too once I come back from exercise. And yeah. So, oh, I was gonna talk about this. I really want to just like do this right now. I recorded this and I wasn't sharing my screen. So what are we gonna say about that? Here's a location of Earth today, based on what we know. Here's the moon. That's the inner solar system. That's the asteroid belt between Mars and Jupiter. Then this is the outer solar system. And the distances here are Sun to Earth. Where's Earth? That's about, how many minutes is that? Is it 8 minutes? It takes light 8 minutes to hit us from the sun. So if you're looking at the sun, that's what the sun was 8 minutes ago. Don't look at the sun directly, please. Just look at it from a video on YouTube or something. All right. Then these distances are in hours. Neptune, Pluto. So it takes like 8 hours. It's like some number like that. I forget exactly to get there. And now this is the Oort cloud. I think this is the Oort cloud. This is not an actual image because the Oort cloud looks very interesting. If you Google the Oort cloud, and this is not on the topic of lifespan, but Oort cloud looks really fascinating. Let me see if I can bring up a Creative Commons image. I am so fascinated by this image. I wonder why it looks like this. Does anyone know? Why of all the shapes does the old cloud look like this? It's either that there is interaction with another system, maybe there's a small black hole in the outer solar system. The solar system is a big place, right? Maybe there's some planetary body there or two. If there are, why haven't we discovered them? Not going into the whole Planet Nine hypotheses. I just find it really fascinating. Like, look at this, the structure of the Oort cloud. Isn't that weird? And I wonder how it morphs and changes. And then, yeah, this orbital eccentricity, the thing Sedna, like, there's a couple of orbits like this, a couple of objects like this. Why are they like this? That makes no sense to me. You're saying that this thing is coming in the orbit of Earth, the sun, and is going, like, the sun is pushing it way out, and then it's still in orbit somehow. Maybe this is a double orbit or something like this. I don't know, right? No, well, if it was a double orbit, it could also go like this. Anyway, I'm not even thinking about that right now. I'm just thinking about the Oort cloud, and we're talking about the. I just find it really fascinating. Okay. Anyway, let's go back to the image. And then you have, once we get out of the solar system, these are the Centauri systems, which are some of the closest solar systems close to us. So if this was Sol, which I think is Sun, then these would be the closest suns to the sun in our solar system, if I can say our, right? The sun in this solar system, then there's all these other. And I've spoken about this in cosmic distance, exoplanets, and the highlighted video on my YouTube page. So distance here in light years is 4.5 to 4.7, 4.6 kind of light years away, something like that. I don't know what the distance to all the other galaxies are. But if something could travel at the speed of light, however relativity plays out, then provided that thing was safe and sound, or maybe just a probe, if it could travel at the speed of light, at the speed of light, it would get there 4.5, 4.6 years. At the speed of light. Okay. Then when you look at the Milky Way, which is the galaxy our solar system is in, and all of these other suns that are close to us, then they all are in this kind of tiny part here. And this Milky Way has, I think, 100 billion suns, like the sun we look up, like we get all the energy. 100 billion, 100 billion, could be less. I think it's 100 billion. It could be more. So now this distance here, let me see if I can draw it. This distance right here is roughly about 100,000 light years. 100,000, 100,000, 100,000 light years across. Now, what happened to my computer? Come on, man. Please keep recording. Okay, maybe I can't even scroll. Okay, we'll just let it do what it wants to do for now. So I don't know if my mouse moving is gonna, okay, it's finally here. So let's add another picture here. Hopefully that doesn't take a long time. So now the distance from the mid of the galaxy to like wherever our solar system is approximately 25,000 light years. I think there's supermassive black hole here. right? So that kind of makes sense. 25,000 years in light years from here, then another 25,000 here. So 50,000 and then 50,000. That's how wide the, uh, well, that's, I guess, if you can measure, if you measure it this way, that would be the width of the galaxy. As you peer out, there are many other galaxies. So imagine how many life forms are in this galaxy alone. Just imagine. There could be life in Europa, in this solar system. There could be life in the solar system. Forget the other star systems. There could be life right here. In Jupiter has a moon is called Europa. It's got liquid water, right? Or maybe Titan. I think Titan is a moon on Saturn, not right, and Europa is on Jupiter, right? There could be life in asteroids, some kind of bacterial life in the asteroids, or maybe on one of the comets, right? There could be life just raining down on us every day. If Dr. Vikramasinghe's theories are true. So I'm talking about bacterial life here, simpler life form, but there's definitely life in these nearby star systems, is my big hunch. My big. I think there's a lot of life in just the galaxy. Tons of life. The life, in my opinion, is teeming with the galaxy is teeming with life, teeming. And I think Dr. Vikramasinghe is right, at least when it comes to this theory. I don't know about all of his other theories. So I think when he says that there is a kind of network of life, and it's kind of like similar sort of origins, I think he's right. And I think there's a definitely panspermia angle to life. That life on this planet has not just been seeded from life outside of the planet, but that this has been happening for billions of years. Billions of years. And we're going to wait and see. You know, we got to wait and look for the evidence. So the question is, when you sequence all these organisms, how different are they from each other? Because Dr. Craig Venter says there's no tree of life. You know what I mean? All of these different species are not connected to each other. There's no master tree of life. So does this mean that, you know, again, does it posit that the panspermia angle is true? And if so, to which degree? I personally think the galaxy is teeming with life, bacteria, viruses, other life forms, plants, insects of different kinds, humanoids at different stage of technological development, and life forms that we cannot even imagine. You know, Dr. Stephen Hawking, I believe, did a documentary with the Discovery Channel. That was a very good application of imagination. And obviously, Dr. Stephen Hawking had a background in physics, so that was a very good documentary, specifically for children who may be watching this. My daughter watching this. And remind me, I'm going to find that documentary for you, and you know, we're going to watch it together. So beyond the galaxy, we have many galaxies. Many galaxies. I'm going to make another video about this. But basically, we have 2 trillion galaxies based on the estimate. This could be lesser if the new data is coming from the mission New Horizons. There could only be several hundred billion galaxies, several hundred billion. So there's 1,000 trillion in a there's 1,000 billion in a trillion. That this number represents 2,000 billion. But if the data from New Horizons is right, then we're looking at several hundred billion. Okay, that means if it is several hundred billion, that means that we are looking at several hundred billion of these in the universe. Whatever that number is 2 trillion, then you multiply all of this with 2 trillion. That means you multiply 100 billion by 2 trillion because there's 100 billion stars in the Milky Way. 100 billion, 100 billion stars, 100 billion. Let me double check this. How many stars are there in the Milky Way?
There are approximately between 200 billion and 400 billion stars in the Milky Way galaxy.
Okay, well, the series says 200 billion to 400 billion. I was saying 100 billion. I don't know which source is accurate, right? I don't know what series. So it looks like series source is Wolfram Alpha. Let's click on that. Yeah, that's 2 billion to 4 billion. 10 to the power 11. 10 to the power 11. Right? 2 billion to 4 billion. I thought it was 100 billion. And it was 200. How many stars are there in the Milky Way?
There are approximately between 200 billion and 400 billion stars in the Milky Way galaxy.
Okay. Thank you, Siri. Goodbye.
You're welcome.
Bye.
Bye for now.
So 200 billion to 400 billion. That's a big number. That means if we go by the total number of planets, sorry, then in the universe, there are 2 trillion galaxies. So you multiply 2 trillion by 200 billion or 400 billion. That's a very big number. That is how many potential suns are there. And then if suns have 4 to 5 planets around them, you multiply that with whatever number we just gave. So that is one set of conditions. And the other set of conditions is the data from New Horizons, right? Then we're looking at several hundred billion. So what does this mean? 200 billion, 300 billion. Then in that case, you will multiply 200 billion by 200 to 400 billion suns in each galaxy, right? So whatever the number is, it's a big number. Okay, that's a big number. That's a big number. I think I could draw it out because it made it sound a little confusing. But we're just going with simple like numbers and plugging into the Drake's equation. If you're watching this for the first time, you might want to look into the Drake equation. This is an equation that was enabled by Mr. Frank Drake, who I don't know personally, but that's what you want to look into. Okay, there's different derivatives of the Drake equation now. So the Sarah-Seager equation is built on top of the Drake equation, the way I understand it. I have some suggestions, if I may, from my non-astrophysics background, because I think the Drake's equation is a very heavy emphasis on the fact that it was spoken on radio astronomy. If you take that bit out and you just replace that with, instead of however I don't remember how the Drake equation is, but instead of saying it's got different entities, right? There's f of this, and there's many entities. And some of the last ones kind of focus on, I don't know what the symbol for that is, but they focus on the radio aspect. No, I'm saying no, don't do that. Just if you swap that with cognitive architectures, right? Cognitive architectures are key architecture. What I mean by this is you have a very simple cognitive architecture. What is this? The simplest one is the thermometer. Well, let's go beyond the thermometer. Slime mold, okay? Slime mold is the simple one I can think of. And actually, some of the slime is pretty smart. I was looking at this last night. They can solve mazes. They know how to search for food. They don't go to the same path. Again, they take different routes to be doing so. Okay, but then you go to more advanced things like obviously insects, plants, right? Insects, plants, other things like that. Then you have things like mammals and like smart birds and stuff like that. And then you have like human level architecture, tool making, predict the future, stuff like that. I think this is not based on the number of neurons. This is not based on the number of neurons. It doesn't look like it. Because there are some creatures like whales and other creatures who have more neurons than humans, but it looks like humans are capable of doing things like making computers, rocket ships, and stuff like that, right? So there's got to be a classification for the minds, and that's what I think we need to swap that in the Drake equation with the radio bit. And I think if you do this classification of mind, however that's going to be done, classification of cognitive architecture, classification of this thing, classification of this thing right here. When you swap this, I think this number for the Drake equation, whatever values it spits out right now, this number is going to go way higher. Because the probability that there are beings in this galaxy the probability there's life of different kinds of galaxies, I think, very high. But if you kind of swap this one thing, I think then we're going to have a higher probability of deducing, at the very least, from a probabilistic perspective, how many life kind of forms could exist that are kind of close to human level, right? And that could be anywhere from, like, they could be hunter-gatherers, they could just be developing language, and to even some who may be more advanced than us. And I think everything I just said, I personally have a strong suspicion, not to sound all that, is true. Okay, so that's my take on the Drake equation. It's a little off topic because the main talk was lifespan. So I'm just gonna I'm just gonna move on for now. Okay, and I'm gonna clear all the drawings, and I'm gonna stop the annotation. So yeah, so these are the galaxies, and then you have clusters of galaxies. So I believe the local group we're part of is in the Virgo supercluster. I could be wrong. But we are in the Virgo supercluster. So I don't exactly know which local cluster we're part of. It is the Centaurus, or I don't know actually. But they're all part of the Virgo supercluster. So I don't know if all of this represents Virgo supercluster. I could be wrong, right? No, it's not all, because there's a Pavo Indus supercluster here. Looks like there's a Centaurus supercluster here. Looks like, and then there's a Virgo supercluster here, and maybe this extends. Yeah, no, this is the Virgo supercluster, and then there's a Southern supercluster, and then there's a Hydra supercluster. So I wonder how many star systems are in these superclusters, because each one of these dots now represent a galaxy, I think. Because now in the previous section you had the local galactic structure indicated, the Milky Way right here, and then that's the closest galactic structure to us, I think. But if it is, why don't I see the okay, yeah, that's the Andromeda galaxy. I think the Andromeda galaxy is going to collide with the Milky Way in I don't know. When will the Andromeda galaxy collide with the Milky Way?
Here's what I found.
I think it's a couple of billions of years out. Yeah, not million, billions. That was a long time. We were probably not even going to be in this universe by that time. Who knows how things work. Right? So, well, think about it this way: 4.5 billion years ago, life on this planet was a goo. Like, it was all mushy. I think I could be wrong with the timelines, but it was very simple life form, like single cell cellular organisms. Okay, so this is the galactic cluster. Then there are the supercluster. So these clusters roll up into superclusters, right? And I wonder how much dark energy and dark matter is in between all this, which not a lot of people understand. So then finally there's the observable universe. And I don't know how relativity works out, but we're like on a speck somewhere in the middle of all of this. So it seems almost impossible for me to think that there is no intelligent life or life at all in the universe. I again think there's life is teeming in the universe. The sheer number of bodies we're looking at, right? And this is another way of kind of conceptualizing. All these images are from the Wikipedia page for the observable universe page, or the shape of the universe, mostly observable universe. I think one image is right here and the other is right here. This other thing that I'm going to show is this is a big image. That's half a gig. Just an FYI, if you're downloading it, be patient. This one is not too big. It's a couple of megs. But this is a logarithmic map of the observable universe. That means as you kind of scale towards the right-hand side of the screen, the distances move in logarithmic scales. So, and these are light distances. So 8 minutes here, 8 hours, something like this here. How long does it take for light to reach from the sun to Neptune?
Here's what I found.
I think it's a couple of hours, maybe not be 8 hours, but it's 8 hours here. But then that's 8 hours in light distance. And then it is 3.5, I think, light years. So if something could travel from the sun towards Proxima Centauri, it would take about 3.5 light years for them to get there. That means you're traveling at the speed of light, not in the rocket ship we have right now. I don't know how long that would take. That would take a really long time. If you could travel from here to Proxima Centauri at the speed of light, you would get there in like, I think, 3.5 years. And same here for Alpha Centauri is 3.7 years. And you know, a little bit more for the other Centauri system or the Wolf system and so on and so forth. Okay, and then the distances are immense. So from this galaxy that we're all part of, which is the Milky Way, and if we want to get to the Andromeda galaxy, I forget how, too much. How far is the Andromeda galaxy from the Milky Way?
Here's some information.
Okay, 2.5, almost 2.6 light years, all kind of, right? 2.6 light years almost. 2.6 million light years, sorry, close.
I didn't get that. Could you?
Bye.
Until we talk again.
So now, say we are on the edge of the galaxy, right? Somehow you made it to the edge of the galaxy, right here. So you were kind of here, and you somehow hopped on a spaceship and you traveled for 25,000 years, and you were in this cryo sleep, you enjoyed your sleep, but now you've been revived safely and securely. Everything is fine, but that took 25,000 light years, right? Because, well, 25,000 years, because you're traveling at the speed of light. I don't know how relativity plays that out. But for you to now get to the edge of Andromeda galaxy would take how much was it? Almost 2.6 million light years. Million. And this again is a logarithmic scale. So the scales are now just gonna explode. There is a lot of distance between, well, galaxies and from supercluster to supercluster. And then you get into all of these other things, which I haven't explored in a lot of depth. But some of these things are massive. Like this thing here, the Boss Great Wall. I don't know if you can see this. The Boss Great Wall, it says right here, the Boss Great Wall, right here. Well, it's getting a little pixely. But the Boss Great Wall is a structure that is, wow, it is 1 billion light years in diameter. 1 billion. Wow. And it has the total mass of approximately 10,000 times the mass of the Milky Way, this galaxy that we're part of. 10,000 times. 10,000 times. 1 billion light years in diameter. 1 billion light years in diameter, which means that when you get to this thing here, this edge, if you want to call it, I don't know what the edge is. Maybe the edge is So actually, what's really weird is they found galaxies here. Like they found a galaxy here, GNZ11. This is really weird because it seems weird that the galaxy formed so early when it comes to the beginning of the Milky Way. But I'm not going to get into that right now. And anyway, so that's I think this is the most distant known galaxy that has been found, GN-Z11. But coming back to the Boss Great Wall, the Boss Great Wall again is 1 billion light years in diameter. 1 billion. The Milky Way is 100,000 light years in diameter. 100,000. 100,000 light years in diameter. I drew a line in one of the, just a couple of minutes ago to showcase, right? So I guess I could, so it's right here too. So this Milky Way is just 100,000 light years in diameter. And we're kind of like somewhere here, depends on your relative position and where you're looking from. But generally kind of depicted, we are like on this end, right? So 25,000 years till the mid of the, to the middle part of the galaxy. It's hypothetically speaking, there's a supermassive black hole here. Seems like there's something there because you don't see like, you know, you just, I think they're just the only thing you can observe. I think I'm not sure, I don't observe, I don't know much about black holes. The only thing you can observe is the radiation seeping out of that, right? So there's something there. You just don't know what it is. But the distance from here to this again is 25,000 light years, and then another 25,000 here. So if you cut it equidistant again, that would be 100,000. But this is 1 billion, 1 billion. There's a cluster. There's a cluster of galaxies here. This is a supercluster, sorry. The Boss Great Wall supercluster identified by this instrument. And it consists of two elongated superclusters. So it's not even a supercluster, it's a supercluster complex that includes two superclusters, two elongated superclusters, two large superclusters, and several smaller superclusters. The elongated superclusters form galaxy walls. So yeah, I haven't explored like this, whatever's in here. I can't read it really well either. It's, I don't know, it's a pixelation or something. But my thought is there is so much stuff, even though all of this is represented by, I think it's something like this. I think it's, I could be wrong on the numbers, but it's 95% between dark matter and dark energy, which not a lot of people understand. I don't know what it is. I think it's 4% just stellar mass. So like the suns within the galaxy, the dust clouds and whatnot, the gases. And then it's 4 point something percent. And then it's, I think it's 4.6 or something like that, or maybe that is 90.1 something. And then there's 0.4% planets. 0.4% represents all the planets. So I don't even know how many planets in the universe. So I think it goes back to this number, right? It goes back to this. But whatever that number comes to, and if you kind of factor in the average number of planets in each one of the galaxies, you kind of multiply those two numbers together in order to be able to get a number. And whatever that number comes to, it's going to be a big number. Doesn't matter which approximation you go with, right? Whatever that number comes to, I think it all represents 0.4% of what we know based on existing knowledge of the universe. Even though this number is 0.4%, I again personally suspect, I highly suspect. Let's go back to the other image. I highly suspect that the universe is teeming with life. The universe is teeming with life. The galaxy is teeming with life. The galaxy is teeming with life. Okay. And the implications of something like this are profound from my very, very humble and uneducated perspective. Because if there's life all over the galaxy and it has some kind of a common origin, right? Whatever that means. Because you're separated by these light distances. You have to appreciate the fact that, how the universe is evolved, there seems to be some separation, unless the just like you have a forest and the microbes are supposedly exchanging information between them, particularly in the root system of the plants and trees, and who knows what else. Maybe there's a bacterial kind of super colony of sorts that is pretty much all over the galaxy, right? So you have a bacterial super colony that is, or you could have multiple bacterial super colonies. So we are kind of like here. So maybe there's a super bacterial colony here, there's another one here and here, so on and so forth. And this could be all over the place. And the question is, if there are these bacterial super colonies, and maybe some other kind of life form, I don't really know, right? Because if you look at these slime molds that they're finding, it's not exactly a plant, it's not an animal. So the question is, how do they communicate with each other, or even do they even communicate with each other, right? So yeah, I think there's there's intricate and very diverse set of life forms, not just bacterial life forms. But if there's some kind of a common origin, for life, right? Some kind of a common, actually, I don't know what that means, common origin. Just this, I'm coming at it from a panspermia angle. I'm totally coming at from a panspermia angle. I think there's something to Dr. Vikramasinghe's theories, right? Vikramasinghe. And he was a graduate student under Fred Hoyle. Now, again, I like I said, I am not. There are many different theories, and I think Fred Hoyle he had an alternative theory to the Big Bang. According to Hoyle, I think the universe kind of has a process of rebirth. However, that I didn't look into that, so I don't know about that, right? So I haven't looked into that. I don't even know what the proposition is, so I can't agree with the other theories. But I think there's definitely something to the panspermia theory, and if this is true, the implications are significant, because we are now one of the life forms amongst the trillions of life forms in just this galaxy alone, right? There could be a gazillion different kind of bacteria out there, viruses, starting with simple life forms. They could be like, many different kinds of diatoms, and it just kind of blossoms from there onwards. There could be kind of life forms that we have no idea about. There could be life forms with a completely different genetic structure. The genetic code is not doesn't follow the same kind of structures. It's not 4 base pairs. It's maybe more base pairs or less base pairs, right? And however, all of that actually results into the enablement of different kind of genes, which are going to then express themselves in different ways. There could be a lot of variety of different kind of life forms out there. So the reason why I'm sharing these thoughts is because I spent a fair bit of time, as you may have noticed if you watch this video, looking into and I don't want to influence the thought by having these pictures in the background, but I'm just going to draw this out right now. My whole thing was about lifespan, and I went with the information that I knew of, and the information that I personally know of is what I have observed as during my limited time on this planet, which is 41 plus years, right? So everything that I reviewed was from the context of what I have observed on this planet. All the things that we looked at, the jellyfish and the worms and the tortoise and the pine cone that, the pine tree that can survive 4,000 years. What else? And that's just scraping the surface, right? Just scraping the surface. So my question is, what kind of life forms exist? Not just, and we're still finding stuff in the ocean. So, with the expeditions to the deep oceans, to Victor Vescovo and James Cameron has done some good work there in the past. But what I'm saying is we're still finding stuff in our own backyard. But what I think we need to think about, that's actually kind of works out. I do the lifespan and now we need to think about what kind of lifespan exists on Earth, on maybe Europa, right? Europa, maybe Mars, who knows? Now they found water, right? Maybe elsewhere, maybe Neptune, maybe Venus, who knows? Maybe stuff's growing, living in caves or something, because we find life living in very harsh conditions on Earth. They found bacteria that can survive for thousands of years without water, or sorry, not thousands of years. Bacteria let me back up. Bacteria that can survive in very harsh conditions in some desert in South America. And we know that there are shrimps near volcanic vent. So we know that there are shrimps living in the near the volcanic ventilation system, right? And the temperature near these vents can be quite significant. So, these species have adapted to thrive in such conditions. Let's take a look at what the temperature is. So yeah, I don't know, like I didn't get a lot of detail. I don't know what their exoskeletons made out of and stuff like that. I wasn't thinking like so much the temperature aspect. What I was thinking more so was that stuff doesn't necessarily have to live on the surface for it to be able to get like direct sunlight and stuff like that. Because we have seen lots of examples where there are like lizard kind of creatures in Europe that can live in caves. You have like obviously the fish and the other creatures that are living like way deep in the in the Mariana Trench. Probably never going to see sunlight, right? And it's like a whole ecosystem that has evolved on its own with bioluminescence and whatnot. And we're just like scraping the tip of the surface. And so when it comes to these shrimps, their source of energy is the volcanic vents. It gets them the heat that they may need, or regulating the body temperature and whatnot. Maybe it's get a little too hot, so their exoskeleton may help control that. But they also get the nutrients that they need, because the nutrients keep getting recycled from the system. And obviously the shrimp cannot live on their own. So there must be a whole ecosystem of microbes and plants and other things that all have this kind of biological kind of, I don't know what the word symbiotic really means. I use that word, but yeah. Anyway, so to come back to what I personally think, lots of life all over the local clusters, then the galaxy at large, and this is not drawn to scale. I'm not saying there's only life in this part. I think there's life everywhere. And I'm not saying there's intelligent life for sure, but I think there's a very high probability. But I would say that life itself, simpler life, bacteria, this other kind of life, many different kinds of life, potential life forms, like I said, we couldn't even imagine exists. But I also think a very high probability for intelligent life. And this life is all over the universe. This is my thought. My final thought is, if there is life all over the universe, I'm going to close on this thought. Okay, I'm going to close on this thought. Let's think about this. If there is life all over the universe, if there is life, if life, then lifespan, in human years. What kind of lifespan are we looking at? So we know they have seen creatures that have a 24-hour lifespan, right? There could be some quantum particles. There could be actually quantum-based intelligent life. And their lifespan would be so slow, like it's fast in our perspective, that, from our perspective, it would be like super fast. But from their perspective, it may be like what our lifespan is. So there could be lifespan like that, right? We already know there's life that lives 24 hours. We used to live 40 years on average. Now we live 80 years or higher on average, 85, 87 years on average, right? That's become the average. The new looks like 130. Let's see. Hope for good things. It's not just lifespan, but also health span. And then we noticed that there are creatures that can live 200 years, like tortoises, jellyfish, pine trees that can live 4,000-ish years, right? We noticed that there's seeds that can sit in, like, what do you call it? Seeds can be revived anywhere from like 2,000 years, some even longer after some kind of therapy was applied to it. I don't know if those are rarefied. And so this is the kind of range we're looking at, right? This is kind of the range we're looking at on Earth. But considering the sheer number of just real estate that we're like witnessing here, my question to anyone who's watching it, what do you think is the lifespan for some of the beings that may be out there, right? So this depends on a variety of different factors, and not to influence your thoughts, but it depends on the environment itself, right? And I just don't mean planets. Maybe there's life living in the middle of black holes, right? So black hole isn't really like this, but let's use. So maybe there's stuff like, there's some part of the black hole, it's called the Kachi horizon. And water do that. And it could be a part of the black hole Kachi. There could be stuff living here. Super intelligent beings, super intelligent beings. And they may have lifespan in the domain of millions of years. Millions, right? Environment. So environment plays a big factor, I think, right? Environment, physical, and also the time-based aspect. And then I think this is a very big range. So the environment factor. If we're talking about life, that the kind of life we've observed it, that would just be a minority of the overall cosmos of life. That would be a very small statistical minority. And within that minority, even there would be huge variances and huge diversity, just like 0.4% of all the universe is planets. And we see so many planets. At least the probabilistic outcome is leading to the reality that there's lots of planets. And so there must be lots of life in these lots of different planets, if the conditions for life are indeed the same, kind of, sort of, right? But what I'm also saying, there could be many different kinds of life. There could be many different kinds of life. There could be life that is made out of pure light, photons, photon, pure light, photons, right? There could be life that has long left its biological and or however this it evolved, and it's in pure light, or it's living in virtual worlds that may or may not still have a dependency upon this world. There may be life that is now multi-universe level. So, they are now at least communicating with or have hooks into all many more universes like this. And then this is the broad spectrum. And then there could be life that is, like I said, so close to let's I don't know if you would have all these distinctions or gradients, but then there would be life that have the same kind of cognitive architecture as us. So I would kind of, for lack of a better word, I would categorize that as humanoid, humanoid life and similar technology level. So their overall technology readiness level would be a certain scale on the Kardashev scale, right? And this even this is a big number. I think this will be a big number. We're looking at gazillions and gazillions of planets. This is a big number. So the question is, what are these beings? What are these beings? What are these beings? What are they doing? What their culture look like? What are their physiology look like? What kind of technologies have they made? And even if they're just 50 years advanced than us in terms of technological adaptation, their world may look very different from ours. 50 to 100 years, their world may look very different from ours. And then obviously there's all of this life forms in it's in it's like, if you keep if I don't know if this is the right way to look at this, but you keep looking at keep looking at the following the chain, or however this all works, then you would see plants of many different kinds, and bacteria of many different kinds, and fungi of many different kinds, and plants and trees of many different kinds, and animals of many different kinds, fish. There could be creatures that we cannot even perceive, right? Somebody hypothesized there's a planet somewhere out there, the atmospheric pressure is so dense that you have some kind of a large, massive creature the size of a whale floating in the thing, right? Or maybe that creature is really buoyant. That's how it evolved. So there's a lot of life. There's a lot of life out there. And one last resource I want to share is, I think this individual does a pretty good job. Let me try to find the resource first, because I don't remember their name. I think it's David Aguilar. David Aguilar, National Geographic. Let me see. Yeah, okay, I was right. Well, I'm surprised I remember this. Okay, so I'm just going to share Safari in this case. So David Aguilar writes terrific books, particularly for children. And I'm going to get these books for my daughter. And actually, they're in the library. I got them. I'm going to get them again. Man, we have a great library system here. We have a really awesome library system. And David Aguilar writes really amazing books. He puts a lot of thought into this. I wish more people would read his books. He makes the models himself. This guy is just so amazing. He's got a brilliant imagination, and he makes all these models himself. That thing you see on the right hand side, that a picture of the satellite looking thing with the propulsion system, he probably made himself, because I've looked at some of his work. And he writes books that are so remarkable and such wonderful imagination. So he's hypothesizing all of these beings of different kinds throughout the cosmos, and he hypothesizes plants that look like butterflies, and trees that have some kind of a circulation system, if I remember correctly. I'm not mixing things up. Just like brilliant, brilliant imagination. That's David Aguilar. And I really think I was gonna uh, talk about Aguilar, but yeah, if you like this kind of stuff, or if you have children, or if you were a child watching this, then you should really check out the works of David Aguilar. Spectacular books. I could not recommend them enough. Okay, so I guess I want to close on that note. And just to recap, today we spoke about well, we kind of scraped the surface of like what's going on with lifespan on Earth, and then we looked at a lot of like we went a little bit like like scrape the detail, like what is it, and what, like, let the hunch guide us. So we looked at um, what what kind of yeah, the links are all over the place right now, but we can talk about that while I have the picture of the universe in the background, I guess. Or let's start with the galaxy, because uh, I don't know if like a mechanism we will get to beyond the galaxy. Uh, so I guess for the foreseeable couple thousand years, we're probably going to be learning more about stuff in the galaxy, unless some breakthrough happens and the way nature of the universe is like truly quantum. So I don't know how all that is going to work, which probably seems like it is quantum. But anyway, so yeah, we spoke about the lifespan and like taking a very local and linear approach to it, because that's really what we know today, right? And then hypothesizing. Well, not hypothesizing. Spent a fair bit of time like looking at like what kind of phenomena is actually contributing to the extended lifespan for a lot of these different creatures. Not exhaustive, but like like all the things I could think of, like in terms of dissection to what's going on, maybe potentially. I kept asking this question: what's going on at cellular level, right? So I'm hoping that our understanding of the cellular structure is going to get much better as more time progresses. Then, kind of looked at life in the animal kingdom, in the plant and tree kingdom, which really there's actually that's the only kingdom there. Plant and trees all rolled up into one kingdom. I don't actually know how many kingdoms are there. I'm going to go and Google that after. But yeah, so we looked at stuff like that. Then we looked at some of the research happening, uh, and what the people at the Methuselah Foundation are doing. We didn't get in a lot of detail there, but from that kind of the past 30 minutes, I made a segue into the cosmos, and I guess my commentary with regards to uh, what I think or highly suspect is out there. And I think there's tons of life, right? So now this opens up this question, like, what does this all mean? What does this all mean? And that depends on your source. That depends on your source. And I don't have particular sources here. I've just been absorbing content here and there. Happy to share what I know. If somebody's more curious or wants to know more, what I was going to say. But I think there's tons of life. And I also think there's tons of humanoid life. And I think the Fermi's paradox, because that like if you talk about active communicating civilizations, right? Drake's equation is supposed to get us that number. And I already shared my thoughts on how there could be some amendment to the Drake equation. But the question is the Fermi paradox. And I think the maybe let's focus it on the galaxy for now, if not the universe at large. But the question is, what if there are so many potential communicative civilizations that are out there? Why is there the paradox? Why is there the Fermi paradox? And the Fermi paradox posits a simple question: if there are so many of them, where are they? Where are they? Where are they? Right? Where are they? And I think the answer to this question is we haven't started looking yet. We have barely started looking. 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 I think that's my answer. I'm coming at a very, very uneducated person. We have barely started looking. And I tell you why. Because, and I think I personally think our advancement is quite rapid. Because if the universe is 14 plus billion years old, billion years, billion with a B, then we have gone from using stone tools, to the best of my understanding, if that is the way history actually happened. It could be that there were many civilizations before Gobli Tepe, and we're kind of like going the cyclical cycle. But I don't know. There doesn't seem to be any evidence. But we have gone from like using stone tools to stone tools to quantum computers. We've gone from this to this in approximately, depends, at least 200,000 years, right? 200,000, 200K, not Kelvin, 200,000 years. So when you compare 14 billion years to 200,000 years, this is like nothing. This is not even like, this is like nothing. So we've gone very quickly, but the thing is, you have to also appreciate all of this time that happened here, time that took to develop language, which probably happened here. But the time it took to develop the neocortex, and that was 200,000 years, and the neocortex grew a lot between this time frame. This is not drawn to scale, but there was a 1 to 2 million year. Now this is 1 to 2 million years, 1 to 2 million time scale, where the neocortex grew a lot. It almost doubled. And then I need to make more space between this and this here. There's a lot of things that happen here. Life evolved on this planet in the past 4 billion years. So then, we have many extinction cycles, and we went from single-celled organisms to multicellular, and then the extinction cycle. Life grew, and there was an explosion of life came into it, and then it shrunk because some extinction cycle happened. And then through many such big and small extinction cycles, somehow we've survived, and we are making quantum computers and other things like spaceships. And I guess what I'm trying to get to is that I think, again, there's a panspermia angle to all this. Panspermia. And I don't think whatever was happening on Earth, not to Earth, however life was evolving on Earth, happened entirely on its own. So I think Vikramasinghe at least is right from this perspective, that comets may have been seeding some code, some biological code, like from place to place, right? Now this is contingent on the hypothesis that the code we're talking about, the biological code, can somehow survive these massive, enormous distances. The only experimentation that we've done here is things like tardigrade, right? Tardigrade or water bears can survive in really, really harsh environments for many years. I think the maximum right now is 3 years. I could be wrong about this. They can survive in vacuum, I think. They can survive in really cold temperatures, somewhat high temperatures. There's a breakout point. But this is the closest we've looked at, like these are called extremophiles. We looked at tardigrade. I shared the example of the shrimp near the volcanic vent. But these are still years, right? Years. And the distance between these real estate is in light years. So the closest one to us is 3.5, I think, or was it 3.4? Well, let's just make it 3.6. 3.6 light years. Light years. Light year distance versus this distance is quite a bit, right? The big question is, if something can indeed survive this enormous distance in a kind of dormant state, and then it gets into a climate, and I don't know the answer to that. The other thing is that maybe there are enough conditions on these comets. There's water, there's something else, for some kind of bacterial colony to evolve into, like, just making use of the recycling, the thing. Maybe they make a little cavity inside and make a shielding, like burrow themselves inside and just kind of keep recycling the resources into kind of like a terrarium. But in this case, these spores or bacteria or something can indeed live on rocks and just keep recycling material. And if that's true, then how much of this are we seeing? How much of this are we seeing in the galaxy? That's my main question. And I suspect that something like this could be possible. I have a strong suspicion. And I think this suspicion of mine leads me to think that something like panspermia is true, maybe true. And I made a video about this many years ago. At that time, my understanding was rudimentary. Since then, I've done a little bit of work here. Not much, but just kind of reading up on. Well, just I'm betting my understanding like what exactly are we talking about in terms of numbers, in regards to what we see, at least in the galactic sense. So, yeah, the implications are profound. If panspermia is true, if this ought to be if this is true, and there's stuff growing in pseudo, not in pseudo, stuff can survive these longer distances on comets, then this must be happening all this time for the past 4 billion years. It must be happening, right? And if that is true, then there must be these local kind of galactic clusters of like colonies potentially. I don't know how they would talk to each other, or these enormous light distances. Maybe they don't talk to each other, but maybe there's something in their genetics or their code whereby they recognize each other, right? Because you can kind of see that just observing animals and insects in general, they recognize each other. How do they do that? What kind of senses power that kind of thing, right? Is it the pheromones or something? What is it, right? So, anyways, I'm gonna close on that note. My simple question to you, again, whoever may be watching, if, oops, not that one. If life, oh, I did the same thing. If life exists, just let's focus on the Milky Way for now. First of all, what do you think? What kind of lifespan are we looking at? What kind of lifespans are we looking at? Okay. And why? What kind of lifespan are we looking at? And why do you say that? Why did you come up with that number? Come up with that number. Okay. That's one question. And my other question is, if you think that somehow there is like this, like there's some kind of communication, not in a radio sense or anything like that, but I'm thinking more like simpler life form, right? Simpler. It could turn out that these bacteria are way smarter than we give them credit for, right? But my other question is, you think if there's some kind of a communication, like some at least means or ability to be able to identify each other, right? Identify each other. If you think that is true, right? Because just look around you, look around your planet, right? Look around your planet, and not again to influence your thoughts. We started on this planet with, I don't want to close, I don't want to get rid of that thing I typed. Well, we started on this planet. It looks like life started on this planet billions of years ago, whether it was seeded from another system or not, most probably was. But it was simpler. It looks like simple, like slime, mold, gooey kind of life. And now life has evolved into so many intricate and different patterns. It's taken a lot of time. But today, the most successful life form on this planet are, I would say it is simpler life form like bacteria, right? Today, the bacteria is found in every single corner of this planet, maybe even in the clouds, who knows, right? And we found that bacteria can indeed dust can travel from all the way from the Sahara to North America, I think, or some crazy distance like that. Maybe the bacteria riding on top of that, right? But we find bacteria everywhere. In the ground, underneath the ground, in the caves, near the volcanic vents, in the desert, in the oceans. Life is full in the ocean. Tons of life, bacteria and viruses. This planet truly belongs, I think, to bacteria, viruses. They are all over, everywhere. They are inside our bodies. There's more bacteria in your body than the actual number of cells. And if you didn't have bacteria in your body, that'd be a big problem. So not only are they all over, but our well-being is directly linked with the well-being of what's going on with the bacteria in our system, the gut bacteria and the other bacteria. Now, bacteria is a different kind, right? I'm not saying go out there and ingest bacteria of like some nasty kind. I'm not saying that. So, I'm saying that this is all over the place, and there's enormous diversity, and we're just beginning to scrape the surface of what's going on here from a bacterial perspective. And I think the other really successful species on the planet are insects, because I think by biomass there's more insects on this planet versus any other species. I could be wrong about what I just said, right? But what I'm saying is, so bacteria have really thrived. They've really thrived. They do, like, there's so many functions that bacteria perform on this planet that I think we're just beginning to scrape the surface. You know, how crucial they are for the plants, for the maintenance of the soil. We're breaking everything down, we're recycling everything. And, you know, it's just super successful, I guess, if you can call them life form, right? Not call them, but I was going to say species, but I switched the word. But yeah, super successful life form. But my question is just kind of keeping that into consideration. Then if that could now be leveraged as a metaphor, then my question is, again, how many other kind of life is there, including just bacterial life? What would their lifespan look like? What is their lifespan looking like? What kind of ranges are we looking at? We're looking at, you know, in human years, anywhere from 1,000 years, maybe? Because we know there's stuff can live for 200 years on Earth, you know, 4,000 years for some trees. So maybe there's some humanoids living 1,000 years or more, right? Maybe it's 10,000 years, right? Maybe it's 100,000 years. Maybe it's indefinite, like I said in Kachi Horizon, right? So I would like to know, why did you come up with that number, right? And what you can be a little imaginative, like what kind of beings are you thinking of? And why? Details are good. We're not going to use your ideas to write a book or anything like that. We're not looking to be the next David Aguilar, but just really curious. Why did you think of that number? And what was the thinking behind that? And the other question I'm interested in, how do you think they communicate? How do you think they communicate? How do the bacteria, if there is bacterial, like, you know, colonies all over the galaxy, then how would they identify each other, right? So, hey, question like this, I don't know if this is anyways, I can go. I hope whoever watched this video enjoyed it, and if anything, the basic amount of not the basic research, but the basic amount of research I did today was beneficial for you, to make you realize that, you know, there's some very interesting species just on this planet. And if anything, if we look at the numbers across the universe, just the galaxy, then it should make us think that what else could be out there, right? And what is that life really look like? Thank you very much. I wish you a wonderful day ahead. Stay awesome, be safe, and do well. Thank you. Stop record.